to start with the motivation. So we can talk about that we have information. So I'll call this knowledge about some quantities which appear in computational models. And these models model something in reality, okay? And then we want to now get the values of these quantities, okay? So we have a good model about this part of reality which we want to have so we can make good predictions. And this is about then making use of observations or measurements of data, okay? So I'm talking about, I have to say now, like if you're doing real experiments, actually this is something which will and can happen all in the computer, that we simulate reality, okay? Or you identify a model which is less refined with one which is more refined, or things like that, okay? These are all things which are possible, all this in framework, okay? So, and it's something which fuses mathematical models and data, okay? So, especially today, and I'll come to a little example like that, it's very fashionable to talk about that we just let the data speak and just make models just out of data, okay? But that, especially in areas of science and engineering, I think forgets all the knowledge which is there in mathematical models. And what I want to sort of advocate here is a fusion of these two things. So we want to get mathematical models together with data, okay? And it should be possible to do this sequentially. So you get one piece of information, you update your model, you get another piece of information, and it becomes even better, and so on, okay? So these are procedures. They can be used for what I was just talking about. They can be used for identification. This is what I was talking about. But they can be taken for monitoring, for instance, let's say a dam or some expensive kind of machinery or whatever, where you have a model and you have a system installed which is monitoring, and the data are coming in and continuously updating your model so that you have an idea of what this piece of hardware is, in what kind of state it is, okay? And it can be used for accident evaluation or after a damage to assess the state and things like this, okay? Good. And it can allow to incorporate other uncertainties and parametric dependencies or whatever, which you might find important. But this, I think it will become clear during the course what is meant with this, okay? So just to give you a short synopsis, this is essentially what you've seen already. So this first lecture will be the basics, okay? So we'll just see what are random variables, expectation, probability, and so on. And the second one is, I think, then it's going to be a bit more mathematical, and this is to get you quickly up to date so that you can do what we call uncertainty quantification. So you have a mathematical model, there's something uncertain in there, and you want to predict the uncertainty and the outputs of this model. Okay? And there's different techniques of doing this, and this will be the second lecture. The third lecture will be by Dr. Friedman, and she will now then do this sort of a little practical examples with you, okay? Second day, this is on Monday. There's only 2 lectures, and they will be both be a bit longer. So the first one on that day is going to be about multidimensional random variables and processes and fields, okay? So this is some kind of reduced order modeling for fields or multidimensional random variables, random vectors, and things like this. The thing is, as you will see, is that you don't want to deal with too many random variables when you do your computations, okay? And this will be all about reducing this number of random variables, okay? These are things which some of you may know, for instance, in other areas from what they called proper orthogonal decomposition and things like this. But this will be the whole thing now here for random fields and processes, okay? And the 5th lecture, this will be the basis now of doing this updating, okay? So we'll talk about what these inverse problems are and how Bayes' theorem is used to do the updating, okay? And then we'll talk about some numerical methods of doing this. Okay? On the 3rd day, this is Tuesday, okay? So we'll continue this. And I'll give you a bit more background on how to do this kind of things and where this comes from, so you know what the connections are and what you're doing there, okay? And the seventh lecture will be picking up on where this lecture left off, and this will be a little bit more on stochastic processes and random fields and what we know about, for instance, covariances and how this affects the representation which we do. And so this has to do with symmetries which these random fields satisfy and things like this. And this is and how these are taken care of, because this is information and we want to take care of this information. Okay, one symmetry probably may be, for instance, invariance against shifts. If the randomness is here the same as a few meters away or something like that. Okay? So we want to see on how to be able to incorporate this kind of knowledge. Okay, and then the third lecture on the day will be again by Dr. Friedman, and she will be doing this, telling you on how to do these UQ on uncertain fields. Okay, good. And on the fourth day, this is the last day, we will sort of, I'll try to consolidate the whole thing to just give you an overview again of what you're doing, why, what are these steps, and talk about a few things which come up typically all the time, which we are sort of glossing over in the beginning, is on what parameters actually to take to update, how to do this with the discrete or the categorical or ordinal, on things like this, how to do this if there are tensors which have to satisfy certain properties and things like this. Okay, and we'll talk a little bit more about a few other methods which we haven't really mentioned here. Okay, and the last lecture is just to rapid everything out and give you an outlook. So because we'd like to, with this course, we'd like to not just that you learn on how to do this, but that you get to where approximately current research is. So this is an outlook and showing these things, okay? And then the last one will be again by Dr. Friedman, and she'll be now using these techniques which we've been talking about here. MCMC is Markov chain, Monte Carlo, ensemble, Kalman filter, polynomial chaos, expansion, Kalman filter, whatever, on how they get done on to do this updating. It's sometimes called also filtering. Okay, good. So this is the contents of the course. So let me start with the course proper. Okay. The first thing is, I think, bringing you some quotes from famous, or maybe not so famous sometimes, people on what they said about modeling. So the first thing is, and you, of course, anyone who's doing engineering and science is clear about that, we use the language of mathematics to do the modeling. Okay, and you go back to Galilei and Newton, they were very clear about this. Okay, so this is to make physical models of something we see in reality. Okay, and typically these models, of course, they are made to predict something. Now, often there will be uncertainty about what is in the models. Okay, and this has also been recognized for a long time ago, of course. So there's again some quotes, again by Albert Einstein, and he says, as long as mathematics, the laws of mathematics, then they don't refer to reality. And if something refers to reality, then it's not certain. Okay, so mathematical proofs is like 2 + 2 is equal to 4, that we're absolutely certain of that. Okay, it's a mathematical proof. But anything in the real world, we're not absolutely certain. Okay, and Bertrand Russell points out that there's different degrees of certainty. Okay, and so what I'm leading you to is beyond doing models, mechanical models for some physical, mathematical models for some physical theory or something like this, we also want to model this uncertainty. Okay, and we want to use mathematics to model this uncertainty. So again, just how do we look at this formally? So we take some aspect of reality, that's what we call the system, okay? And then we try to make a mathematical, we represent this formally, this is a mathematical model we have. And then there is the influence from outside, and this you can call an external action or loading or whatever, okay? Of course, models are judged on how good can they explain something and how good can they predict something. Okay, and so that means that with laws of logic, we have to be able to apply about models of the system and say we can deduce this and this from this and this using this model or something like this. Okay. And we make true statements, and with normal logic, we can deduce further true statements. Okay. But the problem is what to do with statements where we are not certain. Okay, we cannot say they're true or false, but we're not certain about them. Okay, and so we have to build a theory, and this is going to be, in this case here, probability theory on how to do this. Okay, but just a little bit of terminology. System is the part of with reality which we are modeling. Okay, and it has an input, typically some actions or whatever, or some things we're not certain about it, and then we can observe an output of it. Okay, and compare this from our model. We compare this with what happens in reality. Okay. So the inputs are actions or loadings, or excitations, or whatever, or control from outside. And the outputs are observations or measurements of the system. Okay? The model itself is a mathematical representation of the system, which allows you to do this. Okay? It typically has an internal state, and this will become important, that we sort of, the internal state typically cannot be observed directly, and we'd like to find out what it is. Okay? What we call the forward problem is to predict the system response given these inputs. Okay, so this is what you all be loading, know how to do. You have a model, let's say a model of some mechanical system, and now on this mechanical model you apply some loads, then it has some deformation, stresses, strains, and so on. And so this is the forward problem. The inverse problem is, and this is what we're going to be talking about, is you observe the input, loading or whatever, and you observe the output, some deformations at some place or whatever. And now you would like to know what caused it. So what are the parameters in the systems which caused this response? Okay. And there will be two different things. We'll only touch one here is you have one specific system which you want to update. Okay. Or you have a whole family, a whole ensemble of different systems, and you want to identify their probabilistic properties. Okay, think of something which is being produced, let's say some item, a piece of machinery or something like this. So you can take one piece and now try out to find exactly what its properties are, or you can look at the whole production. And of course, one piece is going to vary a little bit from the next piece or whatever, because there is uncertainties in the production. And it's maybe you want to be identifying that. So we'll not be talking about the second part. We only talk the first one. You have one specific system which you want to identify. Okay. Good. So let's go back on how to represent knowledge. Okay. So one knowledge, of course, is data, which you measure from sensors or observations or whatever. That's one kind of knowledge about the system. Okay. And then you can look for patterns and things like that and see what you can do from that. But of course, the other kind of knowledge, and I want to stress this, I think it's just as important as this other one. The first one, as mentioned, is you know what kind of system this is, okay? Because there's many generations of scientists before you who worked on how to model this kind of situation in mathematical language, okay? So I call this structural knowledge about the system, okay? For instance, in a physical system, you may know that physical laws, you don't doubt that they are satisfied, let's say energy conservation or force balance or something like this. So this is a very compressed form of knowledge, and we want to use this too. So we want to use mathematical models which incorporate this together with data which come, okay? So I don't see these two kind of views in competition. I think they're complementary, and the challenge is to combine them. Okay? Good. So just some more quotes of uncertainty. So it's not an easy thing, okay, to deal with them. So Isaac Newton, I don't know whether you know that he speculated in something which was called at his time the South Sea bubble. So people thought there was big riches in the South Sea, and he lost a big fortune. And he said, then I can compute the movement of the stars, but not the madness of man, okay? And Mark Twain pointed out that in the beginning, you're pretty sure about everything. This is this cocky ignorance, okay? And then you realize you don't really know much about it, and this is miserable uncertainty. Okay? So as a final thing of this, of course, is that we realize that really the only certainty is that nothing is certain. and the same is said here by Joachim Ringelnatz. It's certain that nothing is certain, and not even that. Okay, so this is a self-referential statement, and they're the most difficult to deal with. Good. So we want to find a system on how to do this. Okay. So we do the modeling. We make this in a mathematical language, and there may be a hierarchy of models and whatever. And in the end, we want to put the model into a numerical model, which can be run in a computer. And a computer is logic put into silicon and software. Okay, so that's kind of another kind of knowledge which has been in there. Okay, then we have to approximate these models, typically numerically, and we want to assess the approximation error. This is typical numerical analysis. Okay, and there may be different scales of models in time or in space, or there may be different phenomena which we combine, and this is multiphysics, and the other term was multiscale. Okay, good. And we know that the choice of models which we take, that typically contains some things which we are uncertain. So often there are certain parameters or quantities which are in the model, and we're not sure about what their value is. Okay. So these are uncertain parts in the model. Okay. Now, if we look at how classical logic deals with it, classical logic, due to coming from Aristotle, only knows true and false. Okay. And how to derive things from that. Okay. Aristotle already went further, and he had introduced something which is called modal logic. Okay, and this is his possibility and necessity. Okay, but all of this is not really rich enough to capture these grades of uncertainty which we want to reflect here. Okay. Another one which is very similar here from possibility and necessity is fuzzy logic, okay, and probability, and we'll focus on probability to represent this uncertain knowledge. Okay, good. So we're going down this path of probability. We have to first see also that there's different kinds of uncertainty. I'll just take two distinctions here. One is aleatoric uncertainty, where something is random and we cannot do anything about it. Think of measuring, for instance, the instantaneous wind speed in the wind outside. Okay, so the instantaneous wind speed is something which we say is so uncertain, we consider it as random, and even with measuring better or whatever, we will not have better idea of predicting it. So all we can do is talk about the statistics and whatever of this random wind field. Okay, so that's what we call aleatoric uncertainty. If you really look into philosophy, then it turns out the only really aleatoric uncertainty we know today is, physics tells us, is the one which appears in quantum phenomena. Okay, and all the other one should be some kind of explanation, but the view is on how we deal with this. So the aleatoric one, we cannot reduce the randomness by measuring further, but the distinction between aleatoric and the next one, which comes epistemic, this is uncertainty due to incomplete knowledge. Okay, so I may be showing you here three fingers. Okay, sorry, put them here in the front of the camera. Now, if I hide my hand behind my back and then ask you how many fingers I'm stretching out, okay, that's a number between 0 and 5. It's a certain number, but you don't know it. And so that's the uncertainty about the epistemic uncertainty. So it's your uncertainty of knowledge, okay? And there are different proposals how to deal with this, okay? And we'll come to that in a second. Of course, where this is being used and where you may have seen this already is to deal, for instance, with reliability of certain structures, or dealing with heterogeneous materials which are so random, again, that we can only describe them in statistical terms, and so on. Okay, good. Now let's see what are the requirements we have for this kind of randomness. It's especially the epistemic randomness where there is discussions about how to do this, because for aleatoric uncertainty, it's sort of universally accepted that we use statistics and probabilities of frequencies to describe this. Okay, and now, of course, epistemic uncertainty is one uncertainty because we don't know something. But if you could observe what you don't know, okay, then one of the wishes you'd have is that this epistemic uncertainty becomes like an aleatoric description. Okay, so with more and more observations, you want to have something which looks like an aleatoric description. Okay. The other one is you want to be able to have a gradation from false to true. And the things in between are uncertain, but you want to be able to say one thing is more uncertain than something else. Okay, this is what Bertrand Russell was pointing out. And then, of course, there has to be a consistency of your assignment of this ordering. Okay, so the classical logic has to still be true. The combination of statements has to be in a certain way or whatever. So this is the consistency of what I'm referring to. Okay, and we want to be able to aggregate knowledge. Okay, so if we make user observations or we have received new pieces of data or information, we want to be able to incorporate this in our description. Okay, so, and this is so we learn of new conditions, and so this is why this is called conditioning or updating. So we want to be able to do this with our description. And the last thing I want to have on this list here is we want to be able to make predictions, and we want to be able to tell what is it we're going to expect in the future. Okay, because this is important for the making decisions. Okay, for making decisions, we have to know what are we going to expect in the future. Okay, and there will be quantities of interest which come out of our mathematical models, and we want to have something like the expectation of these quantities of interest, so we can use this in decision making. Good. So we can go back historically. Historically, dealing with uncertainty started fairly late. It's only in the 1500s that it really started with. And then it was brought to a first combination by the Bernoullis. The Bernoullis were a whole family of mathematicians. Okay, they lived in Basel in Switzerland, but then some of them moved around. For instance, Daniel Bernoulli was later in St. Petersburg. Okay, and in the beginning, uncertainty was connected with games of chance, like dice or cards and things like this. Okay, and but Jacob Bernoulli was the first one to actually take it further. Okay, and he wrote a book and was called The Art of Conjecturing. Okay, so this is you want to conjecture something about the future, and you want to know how to do this. Okay, these are these consistency rules on how to deal with this. Okay, good. So just to give you a little overview of what has been proposed for dealing with epistemic uncertainty. Okay, we go quickly through this. So this is the mathematical models now of this what we call uncertainty. Okay, and you have to see with all this, mathematical models are just models. Okay, and we have to connect them to the real world by making certain assumptions and abstractions. Okay, and with this we make certain mathematical choices, but they have certain consequences. If we choose something like this and this, then we can or cannot predict certain things. Okay, certain things hold or don't hold, depending on how we make these models. Okay. Now, probability, as we use it today, is something which is very related to the concept of measure of length, or volume, or things like this, or mass, or whatever. Okay, and then one of the things that it is additive. Okay, that's one of the importance. That's the sort of the rule of the excluded third. Okay, so if you have an event PE, okay, and this P of E, this is the probability that this event occurs. And this is the complement of E, that this is that event E does not occur. So the two probabilities that nothing else can happen, either event E happens or it doesn't happen. So the probabilities have to add to 1. So we'll have to make 1 the probability. 1 means something is certain. Okay, and we'll make it 0 means the probability. 0 means this is false. Okay, well, this will not happen. Okay. Good. So some of the models, and then from this we'll derive something which is expectation. This expectation is a linear functional, as we will see. Okay, and this is important, certain things. And we'll see now the probability is one system which satisfies all of this. Okay, but other things have been proposed. For instance, intervals and convex sets. So you just say, oh, some properties in this interval and nothing else. So this is really a degenerate case of probability. You know, with probability 1 is at this interval, and you know with probability 0 it's outside. Okay, so it's a very degenerate case, and you can't do much with it. It's very difficult to do updating and things like that. This is one of our requirements. Okay. Another one which I mentioned already, which has been proposed to deal with uncertainty, this kind of uncertainty, is fuzzy intervals and fuzzy sets. Okay, and the things which appear there is possibility and necessity. Okay, so you see this is something which already appeared with Aristotle and modal logic. The problem is here that there is a problem of having some kind of expectation. Okay, it's difficult to make decisions based on this. Then something which is today called Dempster-Shafer evidence theory, okay, abbreviated DCL. It talks about plausibility and belief. That's kind of an extension of probability, in that plausibility and belief bracket probability, okay? And when data come into play, things which are rhetoric uncertainty, it very quickly comes to probability theory, okay? So in most situations dealing with, I think, physical phenomena or whatever, you probably don't have to deal with this extension of probability theory. In my view, this is more something of when it becomes important, when you have contradicting statements. Okay, let's say a law case, and witness A says this and witness B says this, but not both things can be true at the same time, and how to deal with that. And P boxes is something, these are probability boxes. This is intervals for probability. So this is an uncertain probability, and they can be made even fuzzy. Okay, unfortunately, they're not additive. So we call them capacities. So they're not measures. They don't satisfy this here. Okay, and there may be situations where this is important to do, but not for what we're going to be doing. So this is a quick overview. We will stick with probability. Okay. Good. So let me introduce a model problem. I'll come always back to this model problem here. So think of an aquifer, okay? And what we like to know is how water flows through this aquifer. So there's some porous material, sand, and I don't know, rockies, soil, and whatever, impenetrable layers and whatever. And we'd like to know what, when it rains and the rivers flow on top there, how does the water flow in the underground? Okay. Typically, the aquifers have a much bigger extension in the horizontal than in the vertical, so we can just average over the vertical and make a two-dimensional model. So we make a model like this on this domain. We want to look at this aquifer. We made it an L-shaped domain because this picture looked like this. Okay? And the simplest kind of approximation here is what's called Darcy's equation. Okay, so you say we talk about V, which is the hydraulic head, the pressure actually. And the pressure, the gradient of the pressure drives the flow. Okay, so the gradient of the pressure multiplied with the conductivity, which I call kappa here, that is what is the flow. Okay, and then preservation of mass. So because the flow cannot be created or vanish, we get to this equation here that the minus divergence of this, the flow has to be the sinks and sources. So what is fed into this aquifer or what is taken out. Okay, and this may be either in the domain or on the boundaries. Okay, good. And something which could be uncertain here is this conductivity. Okay, so this is the second picture which makes this clear. So this conductivity would be modeled as a random field in this case. By the way, it would actually be a little tensor normally because we're not certain about that conductivity is equal and also not necessarily isotropic. Okay, but I'll just drop this for a moment here, so we won't go into this right now. And so this could be, think of conductivity being one value here, another value here, but we don't know the values. Okay, of course you can find them out maybe with an aquifer by drilling holes, but then you know it only where the hole was. And in between the holes, you have to make some conjecture. So this is the uncertainty which you have. Of course, you can drill holes everywhere, but then you have a Swiss cheese and not an aquifer. Okay, because the conductivity is positive, yeah, this is the second law of thermodynamics, we'll typically model its logarithm because we want the variables which we model to be free, have no constraints. no constraint like being larger or equal than 0 or larger than 0 or something like that. Okay, we'll come to that at the very end of this course in more detail. Okay, so that's just very quickly why I take the logarithm of this kappa. Good. So this is one possible realization of such a conductivity field. Okay. And what you want to know is, with this whole updating business, to find out what it looks like exactly. So this is something what it really looks like, but you don't know it, and you want to find it out. Okay. Good. And typically you are interested in some quantity of interest. So this could be, for instance, here, the outflow over this boundary, let's say. Okay. This is what maybe you can measure. Okay. And this is what we call a quantity of interest. So it's some integral of some function y, which is a function of quantity with the input, the uncertain quantity, and the state of the system u. In case this is the hydraulic pressure or hydraulic head. Okay, and then integrating over some part of the domain. And typically we have to take the expected value of it. I'll tell you a little bit later what the expected value is. Okay, so this is the quantity of interest. This is something we can measure. Okay. Good. So if you assume that it's spatially constant, it would be just a random variable, okay? And then this is a function of this random variable, okay? So this is called uncertainty quantification. I take this as a random variable and you predict what this expected value is. Okay? This is uncertainty quantification that's going to be doing at the end of the day today, okay? But the other thing, the inverse problem is we observe now this y, not the expected value, but this is what is inside the integral, okay? And we would like to know what is the q which caused it. So that's the inverse problem. This is finding out what is this field here. So what is this field exactly, or what is the logarithm of this field? And once we know the logarithm, of course, we can take the exponential and we add the field, okay? That's called the inverse problem. That's inverting this mapping here, y of q, this function, okay? So that's why it's called an inverse problem, what we're going to be doing. Okay? And there is a certain q, but we don't know it. So for us, the q is uncertain. Okay? And then following Bayesian Laplace, we model this q as a random variable, and we try to identify this with probabilistic methods. Okay? So this is the whole thing what we're going to be talking about. Just to show you an example of uncertainty quantification. So for such a realization, this is a possible realization of such a random conductivity field. Okay, so what you see here is I think a realization of the solution. So just one example for one realization here. What you have here is the mean, the average value of the solution. Okay, here you have the variance of the solution. We'll see what it is here, and this is the probability that the solution, in the solution case is this hydraulic head, is larger than 8. Okay. Not that 8 is some magic number, but it gave a nice picture here to show you what it is. So these are the things you can compute with uncertainty quantification. The examples of the things you can compute, okay? And so this, what we're talking about, goes back to these two people, Thomas Bayes. By the way, it is not certain that this picture really is Thomas Bayes. So yes, but so he was a pastor in England. And he was, at that time, often these clergy were the only educated people. So he worked on mathematics too, and he wrote something up. And this was published after his death in the Proceedings of the Royal Society in London. And this is why his name's attached to this. Pierre-Simon Laplace in France discovered the same thing, actually much more generally a few years later, but not knowing that he published this and then only found out later that had been already, the first examples of it had been already published by Thomas Bayes, so by his friend after his death. Okay, so this is more than 250 years ago. Okay, so just a synopsis of Bayesian inference, or what we want to be doing. So these unknown quantities, they are uncertain, and we model them as random. Okay, so this is, you can consider this as my view. You model this. This randomness is a model of our state of knowledge. Okay. And now comes some new information, some measurement and observation or whatever. And now this has to be made consistent. Our model has to be made consistent with this new information. Okay. And this new information is a condition with which we have to make our description consistent. And this is where we'll be looking for conditional probabilities. Okay. So the idea is we change our model, our present model, but just so much that it becomes consistent, which would have been observed. We'll see how this happens, okay? For this, we have to predict with our present knowledge what is the probability of observing something, and then we have to compare this observation with the actual observation, okay? From this difference, we do the updating. Good, so a schematic representation of this is here. This is the model which describes our physics. Q is now some random field, like in our example, okay? From this, we predict the state. In this case, the state, everything is described if we know the hydraulic head, okay? And of course, for each realization of the log of the conductivity field, there's another hydraulic head. Okay? So we predict all the possible hydraulic heads and their probabilities. Okay, from this, we can predict, for instance, our quantity of interest. These blue dots may be where you drill a hole and look at your quantity of interest. And from this, you do the update. This is the inverse problem. Okay. So this is the forward problem. And then this is the inverse problem from these observations to change this. Okay. So just to show you something which comes out, something we simulated this in the computer. So we take one point in the field where we know the truth is 2. So this was the probability distribution before the observation. And this is afterwards. You see how it's become narrower and focused on 2. Okay, good. So now let's go a little bit of mathematics. So what is a random variable? Okay, so this is the first thing. I'm making this approach to probability by going via random variables. Okay, so this may be not the normal way it's seen in books, but I think it's one of the quickest ways to get you there to do computations and avoid many mathematical details which are not really central to what we want to see. Okay, so we go back to what the Bernoullis did 400 years ago, okay, or 350 years ago. So what do they do with random variables? They essentially dealt with random variables as if they were normal numbers. Okay? They could add them to each other. They could multiply them by a fixed number, okay? Then they could multiply 2 random variables with each other, giving a new random variables. They declared constants also as some kind of degenerate kind of random variables, okay? They just don't vary very much, okay? And they had an idea of how to do averaging, okay? And this is what we will call expectation, okay? So what is to be expected? This is an averaging operation, and it turns out to be a linear operation on these random variables, okay? So what is the mathematical structure which they didn't use at that time, or didn't exist, the theory of that? But today we know that A on B . So my audio was disconnected, sorry. Can you see me? Sorry, something happened.
Cannot see you, but we can hear you.
Okay, very good. So I don't know what happened here. I didn't do anything. Okay, there I am. Can you see me again? Okay, good. So, and now D here, the constants, they will turn out to mean there is a unit in the algebra, okay? Something we can multiply with and it doesn't change anything. And E means that the expectation is a positive linear function, okay? So it's something from the dual space of A, of the vector space A. This is the dual space function of that space. So that's the mathematical translation of what they did, okay? Now I can't change my slides. Question, I don't know, I've lost being the presenter. On again.
Okay, just a minute. Should be okay now, Herman.
Oh, I can't do it. Closed captions. Now.
Is it okay now?
Now it works. Okay, good.
Okay.
Good. So now we're coming to the formal description of what we're going to do. What are the random variables? Okay. So A and B again mean that if we have two random variables and we have a fixed number, that this linear combination is again random variable. Okay. And also that there is a special random variable called 0, which you can add to anything and doesn't change anything. So it's a random variable that will always give you the value 0. Okay. C, being an algebra, means that there, if you have two random variables, there's a kind of multiplication which I denote with this dot here. Okay. And we want it to be an associative algebra. So it means the law, associative law, has to be true. A times the product of B, C is the same as product of AB times C. Okay. And we want this to be a bilinear multiplication. That means the distributive law holds. These are all things you know from numbers and things like that. Okay. There being a unit, by the way, one thing to think of algebras which are not just numbers is to think of matrices, square matrices. You have two square matrices. You can add them and you can multiply them with numbers. It's still a square matrix. You can multiply them with matrix multiplication. It's still a square matrix. This law holds, and so on. There's a unit matrix, which is the unit for multiplication. It doesn't change anything. Okay. And now comes something new here. So this is, we have a linear functional, okay, which is positive. This is in physics, this is called a state. You can think of this, this represents the state of our knowledge. Okay, linearity means this here, and it's normalized. So if we evaluate this functional on the unit, it gives us 1. Okay, that's another way of writing this expected. We call this also the expectation. Okay, the expected value or average. Okay, so it turns out the unit is a random variable which can only take the value 1. Okay, and that's why its expected value is 1. Okay, and when do we call something positive? One is a positive functional, where we call a random variable which is a square, so which is a product of 2 times the same random variable. We call that positive. Okay, so this defines what is positive. When a random variable is positive, it can be represented this way. Okay. And then we want the expected value of that kind of random variable. We want this to be a positive number. Okay? So that means that the functional is positive. This gives us an ordering of the random variable. We can say that A is larger than B if the difference is larger than 0. Okay? And observe, of course, what comes out is the unit is positive. And then there's something a little bit like a unit, okay? A positive random variable which multiplied with itself gives itself. We call this a projection. Okay, so this is idempotent in the language of mathematics. Okay, and it turns out that they're all smaller than the unit and they're all larger than 0. Okay, and when you look at this equation, it's clear the only values such a random variable can take is 1 and 0. Okay, this is why it's called an event. So the event is true when the random variable is 1, and it's 0 when the event is not true. Okay, and we call the expected value of that random variable. This is what we will call the probability, written like this, of this event. Okay. And now, what is an observation or a sample? That's another, mathematically speaking, a functional, which has to be like the expectation, but additionally has to satisfy this. Okay, let's say you observe a random variable A, one of your friends observes a random variable B, and a third friend observes a random variable A times B, then this equation has to be whole. Okay, so that's what we call mathematically expressed as an observation. And then, of course, observing the product is just the product of the two observations. Good. So just a few examples of algebras. Okay, so the real numbers are an algebra like that. Another important one, and this is the one which sort of is the background for all this, is the algebra of real valued functions. So if you take real valued functions on some set, then the sum of some two pointwise sum is again a real valued function. Multiplying with a number is a real valued function. And pointwise multiplication is still a real valued function. Okay? I was already pointing out square matrices are also an algebra. Okay? But the matrices, when they're larger than 1 by 1, they are not commutative. And this is not what we want. That's something you need when you do quantum theory, because then this is still true, but it's not true for your random variables. Yeah? Observing first random variable A and then random variable B is different than doing it the other way around. Okay, so they don't commute. Okay, it turns out that the reals by itself, they are not very interesting because the only projections, the only events we have are the number 1 and 0. So that's not very interesting. And we want to have many events. So you can think of, we're talking about real valued functions on some set. Okay, this is the typical example. I'll call this f of omega. On some set omega, we have the real value functions. And with the pointwise operations, they're in algebra. Okay, and the unit is the function which is always 1. And the 0 is the function which is always 0. Okay, and a function, it turns out, is positive when it's pointwise positive. So it is a square. Remember, before we called it an abstract setting, we called it positive if it's a square of 2 other ones. And but it turns out to be the same if its pointwise positive. Okay, and now this measure here, okay, the probability measure of some event E. So this is some subset we can. So this is a projection. Some other projections how they described. So E is a subset of omega, and we call this again an event. Okay. And we take a set indicator, so a function which is 1 if omega is an E and 0 otherwise, okay? And then we call the probability of this set, we define it to be the expected value of this random variable, okay? So that's the probability measure induced by this expectation operator. Okay? How can we, for instance, compute it? Assume that there is a real valued function, let's say a mass density or something like that. And the integral of this, so it's something positive, okay? And the integral of this mass density, let's say m, that's the total mass. So that's something which is larger than 0 if you integrate over a positive function. And then you can set the expectation of some other quantity, let's say the energy per mass, okay? So what is the total energy? Well, of course, this is the average over the whole body multiplied with this mass density, and then normalized by the total mass, okay? So the probability measure in this case looks like this. It's the density times a basic probability measure, okay? And a sample in this case, when we take the real valued functions, is just the function at one point. It's very easy to see that it satisfies this requirement, okay? So it turns out, we can prove it, I will not do it here, that all these random variable algebras, which are commutative, they can be represented as function algebras on such a set omega, where we can define a probability measure. And of course, we take now the function which is always 1. It turns out that the probability of the whole set omega is 1. Okay, so that's our universe of realizations. This is how we're going to call it. Okay. So one thing which random variables have, which we use them to describe, which comes from the property that they're algebras, is they have what's called moments. Okay, because in algebra I can multiply an random variable n times with itself. Okay, it's defined like this here, of course. I can form polynomials then. Okay, so I take a polynomial and take x of j. I take a to the power j. Okay, so I can take a polynomial of a random algebra. Okay, and the expected value of something like this, that's what you call the moments. So if you take the random variable by itself, you call this the mean, okay? And then is the mean free part is the random variable minus this here, minus the mean. The mean is a constant random variable. And then nth moment is the expected value of the algebra of the element to the power n. And the central moment is if we just take the mean free part, this, and then take the nth moment of that, okay? And then the expected value of a polynomial is just this here, taking the moments, okay? And the same can be done for mixed. So mixed moments are defined as the expected values of a to the power L, b to the power m, c to the power n. This is the moment of degree L, m, and n. And then the same thing you can do for central moments. So moments are just expected values of some powers of the random variable. An interesting thing which comes out is that it defines an inner product, okay? So the inner product is the expected value of the product of the two random variables. It satisfies everything what you want to have for an inner product, okay? And you take as normal, you take the square root out of the inner product with itself and say this is the length. We call this the Euclidean or two lengths, okay? And observe then if they're true, that if the mean free parts we call them uncorrelated, will come later, and a mean-free part is always orthogonal to the unit. Okay? Because everything's orthogonal to the zero. And the variance, now this is one which, thanks to which appears all the time, this is the second central moment. Okay? So you take the random variable, you take its mean-free part, and then you take the second moment. And it's also called sigma squared, with sigma being the square root of this being the standard deviation. The covariance of two random variables, well, that you call the inner product of their mean-free parts. Okay, so, and then we'll say, we'll come to this in a second here. Okay, random variables, we know they're interrupted. So now we have J random variables. We take the subspace spanned by them. We call this the subspace generated by these random variables. Now, because they're in algebra, we can go a little bit further, and we can take all polynomials, multivariate polynomials in these variables. Okay, they also, of course, they're in the set A because they're in algebra. Okay, and we call this, we write this like this, and this is the subalgebra generated by these random variables. Okay? And now, if we have a subalgebra generated by the random variable A and the one random variable generated by B, and we take any polynomial out of this subalgebras, okay? And then if it holds that the expected value is equal, okay, then we call them, for any polynomial, if it's true for any polynomial, we call these two random variables equivalent. This means also that this is zero. We make no difference between them. On the other hand, if the covariance is, again, this is the inner product of the random free part. If this is zero, if they are orthogonal, the random free parts, we call them uncorrelated. And we call this guy here the covariance divided by the standard deviations of these and these. We call this the correlation coefficient. It's something which goes from -1 to +1. Okay, it's like the cosine of the angle between these two. Okay, that's what correlation coefficient is. Now, if this orthogonality here holds for every polynomial out of this generated algebras, okay, so we take a polynomial out of this, polynomial out of this, and then it holds the covariance is zero. That means the mean-free parts are always orthogonal. We call these two random variables independent. Okay, and then this holds here. So it's like an observation, and the expected value of the product is the product of the expected values. That's only true if the random variables are independent. Good. Now the next thing is we want to be able to take functions of random variables. Okay. We've seen already we can take polynomials, a certain kind of functions. Okay. We can also, if it's invertible, the random variable. Okay. Somewhere I pointed out what it means to be invertible. That if there's an element which multiplied with a random variable gives the identity E. Okay. We call it invertible. We can form truncated Lorentz series. Okay. From that we can form rational functions, okay? And by taking limits of for polynomials, we can obtain more functions. For instance, power series like the sine, the exponential, the logarithm, or whatever. We can take Lorentz series and whatever. And it turns out we can approximate sort of every measurable function. For instance, the absolute value, okay? Or the indicator for some subset of R, okay? So that's the probability, turns out then this year. And we can extend the expected value to all these functions. Okay? And now the probability that the random variable is in some subset of R, okay, this is just the expected value of this random variable for the set indicator. The set indicator is a function of this random variable. Okay? And we will call the random variables which have finite variance, we will call this L2 of A. Okay? And we can also for the other subspaces LP by taking the pth power and then taking this norm and taking the closure or the completion of the algebra with respect to this norm. Okay, this is like making from the rational numbers the real numbers. Okay, these are these completions. Good. Some more notions we have to know, and one is the probability we've already seen. So this is the underlying probability measure. We've seen this already. Okay. And so a random variables here is represented by a function on the set omega, okay? And what does it mean to be represented? That means that all the moments are equal, okay? And we call this the law or distribution for an event R, okay, or phi for an event R, okay. And the probability, for instance, that phi is in R, so this is the law or distribution of phi. The probability that phi is in R is the expected value of some function psi, and the function psi is just this indicator function of phi of omega. So phi is the random variable, and then this is the new random variable which takes the expected value. This is the law. This probability measure is called the law or distribution measure. Okay. So it's the probability measure on the real numbers and is carried from the set of all possible realizations forward by this mapping phi, okay, to R. And what is in mathematics called the push forward measure. So there's different ways of writing it. One is like this here. This is probability, this random variable is in there. That's sometimes written like this. So this phi with a star below means the push forward. It's sometimes written like this. This is kind of the definition what it is. So it's probability of those elements there that phi of omega is in R. Okay, good. So it's just two more things or notions to explain, and this is now what are the distribution functions. So, and we start with a cumulative distribution function. Okay, I hope many of you have seen this. So this is just to get you into the notation here. If we have a random variable a, okay, then this is just the probability of this random variable being less than x. This we call f of a of x, and this is what's called the distribution function. Okay, and of course this is taking this set and then its indicator and its expected value of that indicator function. Okay, so this is the distribution function, and it's clear that is the limit as you go to minus infinity that it's 0. Okay, that it's ordered like this, so it's growing, it's not falling, it can only grow. Okay, and the limit as you go to 1 is 1, to infinity is 1. Okay, and the probability of a random variable between y and x is the probability, push forward probability of the set, and it's just a of x minus fa of y. Okay, and you see differences play an important role if we want to compute these probabilities. That's why we look at the derivative. That's the extreme case of these kind of difference. So we call the generalized derivative, we call the probability density function. Okay. So equivalent random variables, remember these are random variables which had all the same moments. They have the same cumulative distribution function. And they have all, if it exists, the same derivative, the same probability density function. Okay. So we can compute this here, which was here now, we can compute it by integrating over the density from y to x. Okay. And the probability that A is some set E is just the integral over the set E of the density. Okay. And this means that the expected value is this here. You take C times the density and integrate over the reals. Okay. And the higher moments by taking C to the power n and so on. Okay. And for any function, you can compute the expected value of the function now in this way by integrating the function times the density. Okay. Good. So we'll come now to a few pictures to explain this here. Okay. So these are the last two slides, I think. And so one is to look at the commutative distribution function. The way I've defined it, it's what's called a Kadlak function. So this is short from French, meaning continue à droite, limite à gauche. Okay, so it is continuous from the right and has a limit when you come from the left. Okay, and it's monotonously increasing. Okay, so it looks like this. So the full dot belongs to the function, the empty dot does not belong to the function. So this is a probability computed function from a discrete random variable. This random variable only takes certain values. Okay, and this is where the jumps are. Okay, so it takes the value xj with probability pj, and then formally the density would be a train of delta functions. Okay. Now this is a continuous random variable. There is no jumps, so that's a normal function. Okay, which then has a generalized derivative. Okay, and this is a mixture of both of those. Part is continuous, part is discrete. Okay, so you call this an atom here. Okay, because everything sits there at this point. And the inverse of this cumulative distribution function, so this is an example of such a function, and you would have to flip this along this 45-degree diagonal. What you get there is a quantile function. So it's kind of the inverse of this. Because this is monotonic, it has kind of a generalized inverse in this inverse function. So the opposite probability P telling you where you are. That's called the quantile function. Okay, and three more notions which I have to introduce before we stop. One is the mode. So this is where the PDF, the probability density function, has its maximum. Okay, so what you see here is one where there's only one mode, but we can have probability densities where there's several, then we call this multimodal. Okay, and every peak of the PDF is a mode. The median is a very special quantile. Okay, so this is where the quantile function, this is the quantile function at 0.0. 50% are left of it and 50% are right of it. Okay, the probability that it's less than this here is 0.5, and the probability is larger than this is 0.5. Okay, and what is the mean? Is this picture? Well, that's the center of gravity if this was a mass distribution. Okay, then it's where you put a scale here and it would balance. Okay, and what you see here is a few more what's called quantiles. So these are their numbers here. I think I have to blow this up here a little bit. And then I'll move it here. Okay. So Q2, this is the median, and Q1 and Q3, these are what's called the quantiles. So there's 25% here, there's 25% here, there's 25% here, and there's 25% here. Okay. And get it to normal size again. And so you can have, these are quartiles, okay? It's a particular quantile, and you can have quantiles of any kind of probability. Good, so that's the end of the first lecture. I think I've gone 5 or 6 minutes over time, so that may be moments of higher order. So Angelica asked what moments of higher order can tell us. So let me go right away to, this is on slide 33. Okay. So, what can tell us? So one thing, what they can tell us whether it's going to be, the first thing where it's going to be used is the variance. So that's the second moment of the mean-free part. Okay, so they're there to characterize the random variable. Okay, so it's because the random variable is not just characterized by its mean. So we have different ways. We'll come to this in another lecture on how we can characterize this. One is to characterize a random variable by all its moments. Okay. So if we know all of its moments, then we know a random variable. Remember, we call two random variables equivalent if all the moments are equal. Okay, so the moments if you know all the moments, then you know the random variable. We have to find different ways of knowing the random variable. The moments are one way, and the distribution functions here, knowing this function here is another way of knowing it, or knowing the density is another way of knowing the random variable. Any other question? Doesn't seem to be the case. So then let's stop here now and make a little break till 10:20 now. It's only 11 minutes till then. So everyone can have a drink of tea or coffee or something like that. And then we'll start punctually at 10:20. Okay?
Okay.
Good. I'll switch my microphone off now.